Okay, so let's quick review from what we talked about. I guess it was Friday, huh? Yeah, it didn't seem that long. It seemed longer. So what about this? If we want to factor these, remember we talked a lot on Friday about just why do we factor? Reminded ourselves that the whole point of factoring is just so we can use the zero product property and set them equal to zero and find the solutions. Okay, we talked about how when we're looking for, we talked about a lot of stuff. We talked about when we're looking for real solutions, why sometimes we can't just isolate anymore with these big polynomials. We gotta, if we're looking for, now most of the time we're just gonna be looking for real solutions. But we still don't know all the rules associated with doing things like, like this. If we have x to the fourth equals 8, we still don't know how to take roots other than square roots of both sides. And so that's sort of off the table for now. It's going to be on the table next unit, and then that'll give us some additional, maybe even some shorter shortcuts. But for now, that's sort of off the table, and we're just looking at factoring stuff. Okay, so let's factor this, and that's all I'm asking you to do is factor. We're not solving it. First I'm going to have you guys just work on just the factoring stuff, and then once you've got that down, the solving, there'll be an assignment where you can use factoring to solve some equations. That'll be easy then. That makes things actually easier rather than harder. Factoring is the hardest part. You get through, you get this figured out, you're set. This is the one that we know how to do right now for a function bigger than a quadratic. We only talked about one pattern or one group of patterns, the sum and difference patterns. Okay, so how could we do this one? Suggestions? We could take out an x, yeah. So if I take out an x, let's see what happens. If I factor out an x, I'm left with x times the quantity 81x cubed minus 24. Okay. Now, what's the only hope really of being able to factor this? Which one is the only possible one it could fit? Tell you what, let's review our patterns real quick. While we're at it, we know we have a couple patterns. You're going to have to memorize these, of course. I will help you do that with a little assignment. But what are our patterns? So how about the squares? What is the factoring pattern for a difference of squares? Let's do a squared minus b squared. What does that factor into? Okay, say it again. A plus B, A minus B. So that's our conjugate pattern, right? Good. How about this one? A squared plus B squared. What's that? Remember this one? Say it again.
A plus B times A plus B.
Wait, that one doesn't do it, does it?
Doesn't factor. Doesn't factor, right? Okay, how about A cubed minus B cubed?
A plus B.
Yeah, we know we're gonna have a linear and a quadratic, right? Now, let's put in the terms first. What are the terms? So I get A,
B.
B, A squared. Okay, now let's just put in the signs. So what goes there? Nope. It's whatever is there, right? So if that's a minus, that's a minus. Plus. And then remember the last one is always plus because any number squared is always positive, right? Does that make sense? Okay, so then how about A cubed plus B cubed? Same pattern, right? So how do the signs go? A plus B, A squared minus minus AB. There you go. Okay, so those are the patterns that we know. That's it, right? So what's the only pattern that could potentially fit? Well, which one of those patterns? Is it a sum or a difference pattern? Difference, and it's a difference of? Well, the only one it could fit, possibly, would be cube, right? Difference of cubes, because I've got an x cubed there. But the numbers don't really fit very well, do they? Is 81 a perfect cube? No. Is 24? No. What can we, any suggestions? Say it again?
Divide both by 3.
Well, we can't divide by 3, we could factor a 3 out, couldn't we? Right? So we could factor out an additional 3, and then we're left with 3x out front. This leaves us with 27x cubed minus 8. Is that better?
Yeah.
That is better, isn't it?
3 to 2.
Right, so now we can write this as, well, we've got our greatest common factor. We've got this monomial factor out front that's done. But then how about in here? This is our a, isn't it? Right, so we've got to find out, what thing could be cubed and give us 27x cubed as a result.
3 and 2.
Okay, so that's going to be, this is going to be a 2, isn't it? This is going to be a 3.
Yeah.
It's not just 3 though.
3x.
3x, right? The quantity 3x cubed is just 3 cubed times x cubed, right? So that works. This is like our a minus b cubed, right? And so that's got to equal, we know the pattern, a minus b times a squared plus ab plus b cubed, right? So then, oh, it's b squared, I'm sorry, b squared, yeah. You're right. What I was thinking. Okay, so then we end up with, if we just match this stuff up.
Yeah, put the cube back.
Oh, oh my gosh, I did. My brain is not communicating with my mouth here. There,
Yeah.
finally. I can write it too. Okay, so if we match this stuff up, then we're just going to get, there's our 3x from out front. And then all this stuff, we got to write in terms of our symbols and our problem. It's not an a and a b for us, it's a 3x and a 2. So what's this going to be? 3x minus 2, good.
3x.
Okay, so 3x quantity squared, right? Plus okay, so, and then we gotta put that. So we've got our 3x times our 3x minus 2, and what does this whole thing simplify to? What is the quantity 3x squared, because that's our a squared? Okay, so we get a 9x squared plus
No, you wouldn't be able to, right?
6x, good, plus, good, okay, and that's it. No, we don't want to distribute anything because that's what we were just trying to undo was the distribution, right? Remember, distributing would be expanding. We're doing the opposite of that. We're trying to break stuff apart into small pieces, okay? All right, so let's just say hypothetically here, if this thing had been equal to 0, if we'd been solving an equation, what would our solutions have been? Just to kind of glance ahead just a little bit. What would this factor have given us when we apply the zero product property? If I'm looking for the solutions, the values of x that would make this true. Remember what we do with the zero product property. Once we write it as a product of factors, we can just find the zeros of the individual factors. So for what value of x is 3x equal to 0?
0.
0, yeah. So x equals 0 is one of our solutions. Now, you're going to notice, if you haven't already, that anytime you factor out a monomial with an x in it, so a greatest common factor that's got an x in it, that always leads to a solution of 0, doesn't it? Okay. What about this one? X equals 2/3. What about this one here? Does this give us any real solutions? We could check it and see. Let's just check if it did, we would just use the quadratic formula, wouldn't we? Right? Well, what's the discriminant that we get from this quadratic equation? If we set this factor equal to 0, we get the equation 9x squared plus 6x plus 4 equals 0, right? So let's just check the discriminant. If it turns out that it's positive or 0, we'll just use that in the quadratic formula. But what are we going to get? The discriminant is what? 36, right? 6 squared. So 36 minus 4 times 9 times 4. Well, that's pretty obviously negative, isn't it? Right.
Maybe 1 over 9.
So that means we're getting, if it's negative, we get how many real solutions out of this
0.
quadratic equation? 0. Is that a surprise to us? No, didn't we say that on Friday? That whenever you use a difference of cubes or a sum of cubes pattern, you always end up with an irreducible quadratic factor that never has real zeros. They're always imaginary. Okay, so this one we don't even have to try. We automatically know that I'm getting 0 real solutions out of that. There's going to be 2 imaginary solutions. And so typically on the assignment, we're just going to be looking for the real solutions. So there they are, there's 2 of them. Okay? All right, so here's some good news. The next kind of, well, before I move on, this is going to be the strategy that we use whenever you're factoring a polynomial that's got 2 terms. If it's got 2 terms, the terms are either added or subtracted, right? And so it either is going to fit a sum or a difference pattern. That's it. Your strategy for factoring a polynomial with 2 terms or solving a polynomial equation where the polynomial has 2 terms is that. That's it. Sum or difference patterns. End of story. Okay? What's kind of nice about this is the strategy that you use is solely determined by the number of terms in the polynomial. 2 terms, covered. What about 4 terms? We'll do that one next. 4 terms actually is already covered. You know how to do it. You don't know that yet, but you do. The same strategy we used when we factored quadratics where a was bigger than 1 involved this strategy, factoring by grouping. So let's look at an example. What if we have something like this? How about? I want to factor this, right? It's got 4 terms. The only real, at this point, strategy, the only viable strategy for us at this point is just to try to factor by grouping. And either it's going to work or it's not. Okay, now, the ones that you're going to have are mostly just going to work because they're sort of handpicked to practice this skill. They won't all work in the real world, of course, but for now, that's the only strategy that we have, is factoring by grouping. So let's try it. Okay, so we would just group this into 2 terms. It honestly doesn't, well, yeah, you want to start with the polynomial in standard form. Let's just say that. So first group, in this case, consists of the 10x cubed plus 20x squared. Second group is the x plus 2. How did we factor by grouping? We've done this a bunch. What did we do to this first group?
Factor out 10x squared.
Okay, we factor out the greatest common factor, which is what?
10x squared.
leaving us with what?
Yeah, x plus 2.
X plus 2?
Yay, and it's
Okay,
all
questions?
happy. So it's
Okay.
x plus, it's 10x squared plus 1 times x plus 2.
Right, now remember, if this is going to work, if it's gonna work, this has to be the same leftover that we get over here. But we don't know it's gonna work this time, right? We really don't know it's gonna work. Well, we're gonna assume it does, and if it doesn't, we won't be able to find a greatest common factor that fits. So the way we would do this is we would just write an x plus 2 there, and now ask the legitimate question, is that possible? What time is there something that multiplied by x plus 2 equals x plus 2? Yeah, 1, right? And so it did work this time. And the answer we got was, let's factor out the common factor, which is the x plus 2. And then we're left with 10x squared plus 1, right? Okay, now, this is obviously done, right, because it's linear. This one is not obvious, well, I mean, maybe it is to you now at this point, but because this is an x squared, this is a quadratic factor, we'd always have to ask ourselves the question, okay, can we go further? Could we break that up into 2 pieces? Can we? We can't, can we? The only possible pattern that could fit, it's a sum of 2 terms, right? And based on we always want to look at the variable, right? So we have an x squared here and no x here, so it would have to fit a sum of squares, but remember, there's no such pattern. So it can't factor, right? It's impossible. So that's done. That's fully factored. Okay? Do you see that wouldn't have necessarily worked if this had been, like if this had been, for example, a 3? It wouldn't have worked, right? Because then there's nothing we could multiply by x plus 2 and get back x plus 3. And so we could not have factored it that way. Okay? Let's try another one of those. Hope I did that right. I think I did. We'll see, I guess. If it doesn't work, and we practice one that doesn't work. So what do? Group them? Everybody agree? Anybody disagree? I could. I can group these. Oh, okay, good. I was gonna make you do it twice then. This would work to factor by grouping, but when we get done factoring by grouping, guaranteed, there's gonna be more factoring to do. Because we could factor out a greatest common factor initially, couldn't we? Always wanna do that if you can. So what can I take out initially? 2x, yeah. Okay, so we could take out 2x, leaving us with, what?
3x cubed plus 4x squared minus 12x.
32 is 11.
16? Okay. All right, so now what? Now group them, right?
Yes.
Okay. So that's going to give us 2x times first group, 3x squared plus 4x squared plus the second group, right? And the second group is our negative, yes, oh, cubed, gosh, you have to watch me like a hawk, don't you? Cubed minus 12x minus 16, there we go. Is that right, I'm hoping? Okay, so now what?
X squared.
Okay, good, so from the first group, we could factor out, best we can do is an x squared, leaving us with
3x.
okay, good. And then, what next? Well, what would I write next? If pretend you're doing this problem, what's the next thing you would write? Good, okay, a blue 3x plus 4. Knowing full well that that may or may not work, now we just gotta see, can it work?
Yeah.
Yeah, it can, with a negative 4, can it? Good, okay? So, we get 2x times what? Okay, good, we're gonna have an x squared minus 4 left over when we factor out from each of these two terms our 3x plus 4. Good, so how about that, we done? We done? No, Hunter says, how come?
Because x squared minus 4.
X squared minus 4 is a difference of squares, isn't it? Right? That's the same thing as x squared minus 2 squared. And so that actually breaks apart into what? X minus 2 times, no, plus 2. There we go. Okay, and now, whoops,
Oh no, it's not blue.
gotta be blue. There's our fully factored form. How about that? Okay. So if this had been a function or an expression that was set equal to 0, if we were solving an equation, what would our zeros be? We'd either end up getting x equals 0, okay, or x equals 2, or x equals negative 2, or x equals negative 4/3. Good. Okay, now, if this were a problem, and once again, I'm not really giving any of these right now, but if we were solving an equation here, would we have maybe even done that last step, factoring? If all we're looking for are the solutions. Haley's saying no, and I like that. How come? Okay, because at this point, if we're just trying to find solutions, if the instructions are not to factor this thing fully, but just to find all the real solutions, look what we could have done. We could have set this one equal to 0, sure, and gotten that solution. We could have set this one equal to 0 and gotten that solution. But we also could have just set this function right here equal to 0, right? And x squared equals 4. Is what I'd get back when I set that equal to 0, right? And what are the solutions of that? Plus or minus square root of 4, right? So that would have been quicker, right? Everybody agree? Okay? All right. Good. So then this is it. This is it for all the factoring stuff. There's one more. And this one is also, I think this one is not too bad because it also is just stuff you already know. It's just kind of a different look at some things you already know. So what would you do with something like maybe, tell me what your thinking is, for something like this. What if we're supposed to factor 16x to the 4th minus 1? Okay, what do you think about that? Now, I did not give you any difference of fourths, or sum of fourths, or difference of fifths, or sum of, I didn't give you any of that stuff. You gotta stop somewhere, and the most useful ones are just sum and difference of cubes and difference of squares. So I didn't give you necessarily the tools to do that one directly, but you still can do it. How? Can I see that as a pattern that I do know? Of the sum and difference patterns I already have, which, there's only one of them it could possibly fit. What would that be? Say it again? Well, okay, difference of force, that we don't have that one. All we have of our difference patterns are a difference of squares and a difference of cubes. Now, once again, focusing on the variables, x to the fourth. Aha, we could make this a difference of squares, couldn't we? If we rewrote this a little bit, 16x to the fourth, I could write as something squared, couldn't I? Right? This could fit the pattern. This could fit the pattern a squared minus b squared if my a is what? What squared is 16? 4. What squared is x to the fourth? Uh-huh. You see that? So the quantity 4x squared gives us back 16 times x to the fourth. Yeah, you betcha. Go ahead. And then, of course, what's b going to be? 1. Right? So how about that? That fits a difference of squares pattern, and that allows us to factor this at least partially, right? And so what's that going to give us then?
X minus 1, y squared.
So 4x squared minus 1, good. And so that's, and this is just, isn't this just a minus b, right? So what's a plus b? Okay, good. Now we broke it into smaller pieces that maybe we can deal with more directly. Okay, how could we deal with this first one? What pattern is that? That's another difference of squares pattern, isn't it? That looks like a squared minus b squared. What's my a? 2x, good, because it's got to be the quantity. What quantity squared gives us back a 4 and an x squared? Oh, 2x, and then that's obviously just a 1. What about this one?
Just factor.
Doesn't factor. That would be a sum of squares, and so it doesn't factor. Good. And so we end up with then, what does this difference of squares pattern give us? 2x minus 1, 2x plus 1, and then we've still got our 4x squared plus 1 that's irreducible. It's stuck at that factor, doesn't go any further. So if this were an equation we were solving, what would our zeros be? X equals 1/2, or, yeah, really, it's just going to be plus or minus 1/2, isn't it? Right? Okay, so what would we call that? Well, kind of the technique that we're using here, this is, I mean, really, we didn't do anything new. This falls into the category of that first class of problems that we looked at, because it came down to a difference of squares, didn't it? The only thing I would say is unique about this one is that we took advantage of the fact that this really did fit, even though it started off with a 16x to the fourth minus 1, it fit a pattern that was quadratic. Difference of squares pattern is really a quadratic pattern. Something squared minus something else squared. You think when we talk about the squared, that's quadratic. Okay, can you use a similar strategy for something that is not a sum or simple sum or a difference pattern? How about this? What if we had what if you're supposed to factor that? Okay, what does that kind of look like?
We can factor out an x squared.
Okay, it's something, this looks an awful lot like what we did last chapter, doesn't it? Right? Now, last chapter, we would have done a problem just like this, but it would have been, let's separate the board here. This is chapter 6 on the left, this is chapter 5 on the right. We might have seen this before, and maybe it was, instead of x's, so we don't confuse ourselves, let's call it like z was the variable. But this would have looked something like z squared plus 3z plus 2, wouldn't it? And that would have been pretty easy. How does that one factor? Are there magic numbers that multiply to c and add to b? 1 and 2, yeah, it just would have looked like z plus 1 and z plus 2, right?
You split that one in?
That one really is the same pattern though, isn't it? Right? What's the difference though? Here we just had something squared plus 3 times something plus a constant. Here we've got something to the 4th plus 3 times something squared plus a constant. But the coefficients are all the same. So how could we have grouped this so it looked like a quadratic pattern? How could we have written this as something squared plus 3 times something plus 2 so it matched the form that we were used to in chapter 5? What would the somethings have to be? What? They would just be x squareds, wouldn't they? So really we've just kind of broken this down into packets, if you will, of x squareds, right? But it still factors the same way, doesn't it? Because a quadratic trinomial is a quadratic trinomial. As long as it fits this pattern of something squared plus 3 something plus 2, that factors with this pattern. Whether you call them z's or x squareds, it doesn't matter, right? So this has got to break up into z, which is just an x squared, plus 1 times z, which is an x squared, plus 2. Right? See that? Can I go any further with those? I can't, because those, the only pattern they could fit doesn't exist. Sum of squares. Okay, try another one. Like that. How about this? What if we have any suggestions for a good first step here? Factor out of 2. Good. Good. That's a great idea because then it takes us from the dreaded a not equaling 1 in a quadratic trinomial to a equaling 1, and that's a much, much easier proposition. So we take a 2 out, then we're left with x to the 4th plus 5x squared, good, plus 6. Okay. So now, and sort of the what gives this away here a little bit is if I've got an x to the 4th in my first term and an x squared in my second term, why not think of those in quantities of x squared in the first case, right? Does that make sense? So we break this up into 2 times, what's this going to be? X squared squared, right? Plus 5, oops. X squared plus 6, right? So yeah, it's in pieces of x squared, but that just looks quadratic, right? I got something squared plus 5 something plus 6. Are there magic numbers that fit that quadratic trinomial? 3 and 2, yeah. Right, so this breaks up into 2 times x squared plus 3 times x squared plus 2, right? Can I go any further? Nope. Get the idea? Okay. What do we have here? Let's try one more of those. All right. How about can I factor out a greatest common factor? No, so I'm stuck. I'm stuck with an A times C then split B problem. Worst case scenario, perfect storm. So what is AC? Say it again. 30. Okay, what two numbers multiply to AC and add to B? 30 and 1. Okay. Okay, so what's that mean? How do we split B in this problem? Okay, so the 31x squared term is the one that gets split, isn't it? So we end up with then 5x to the 4th plus, what two terms? 30x, either order, doesn't matter. So 30x squared plus x squared, good, plus 6.
Okay, you just put them.
Now we just group them, don't we? Right? So now we group these first group, second group. This time we know it has to work. We know factoring by grouping works this time because we had magic numbers that work for us, right? We were able to split B. And so what do we get then when we factor
5x
this?
squared.
5x squared times what?
So x squared plus 6.
Okay. Plus,
Same thing over there. So you,
what times x squared plus 6 is x squared plus 6?
1.
1. Okay, and so what does this factor into? Okay. Okay, good. So we can pull the x squared plus 6 out of each term, leaving us with 5x squared plus 1. Can I go any further? No. You got it. I'm convinced. Okay, so that's it. That's going to be what I'll do, just so you kind of know what's going on then. I will give you, prior to spring break, I'm going to give you one more factoring assignment, which is going to be just practicing the stuff we looked at today. Not a lot of problems. And then the next step would be, we'll just go back and give you an assignment, which I won't expect you to do before spring break, that's for sure. But one where you're just going to solve some, you have to pick which one works. Which technique you're going to use, just solve some polynomial equations using those patterns. And that's most of the rest of the chapter. That's probably the biggest bulk of chapter 6 is this. There's one other issue that's it takes some time to go through, but really this section is kind of the heavy hitter from chapter 6, and then it's all downhill from there. Okay? Sound good? All right.